So when you're going to add or subtract fractions, you're looking for a common denominator, and you have something really tough like 9 and 30 that you're trying to find common denominators for. You can always factor. 9 factors, and factors are just numbers that'll divide into it and then what's left over. 9 can be divided by 3 and you'd be left with 3. It can't be divided up any further. Those are what we call prime numbers. 30 can be divided by 10, which would leave us with 3. 3 is prime. It can't be divided any further. 10 can be divided up into 2 times 5. Those are prime. So if we're looking for a common denominator, 30 is equal to 2 times 3 times 5. I'm just putting them in order from smallest to largest. 9 is equal to 3 times 3. And what we look at is what they have in common first. They both have a 3 in common. That's it. Now, the 30 has a 2 and a 5 that the 9 does not. So the 9 needs to have a 2 and a 5. The 9 has a 3 that the 30 does not. So we need a 3 up there. What we have done is we've made sure both of them have all the same factors. And what we've done is we've created the least common denominator, or least common multiple. If I multiply those together, 2 times 3 is 6, times 5 is 30, times 3 is 90. Well, 3 times 3 is 9, times 2 is 18, times 5 is 90. So that's telling us that 90 would be the least common denominator, least common multiple of 9 and 30. Now that was kind of a long way to go about it. You can always make these lists. Like I said, count up 9, 18, 27, 36, and then the 30, 60, 90, and come up with numbers that match up. But if that doesn't work for you, if you need an organized way of doing it, factoring works as well. The other option you have is you just do 9 times 30 is 270, and you could use that, but you'd have to reduce when you're done. Yes, sir.
What I tried was, I thought it was 90, so I just did 9 times 10.
Yep.
And then 3 times 30.
Okay.
Was that on the right track there?
That's the right track. So 9 times 10, so 4 times 10 would be 40. 30 times 3 is 90, so 7 times 3 is 21. And we are subtracting, so 40 minus 21 is 19/90ths. 17, this is a 0, this will be 17 minus 9 is 8, so 8 19/90ths should be the answer. You bet. Now that I've let you spend a week working with fractions, I'm going to show you something on your calculator. Unfortunately, the calculator I have is a graphing calculator, and the graphing calculator doesn't have this function, but there's a button on your calculator that makes these fractions way easier. Depending on the calculator you have, if it's the Texas Instruments, you should have this button, ABC. If you wanted to enter 17 and 4/9 minus 9 and, what was that, 7/30, that ABC key could save you a lot of work. What you would type in is 17, hit the ABC key, then 4, hit the ABC key again, and 9. What you just entered was 17 and 4/9 minus 9, ABC 7, ABC 30. Hit equal, and it should spit out 8 and 19/90. I had to make you struggle for a week on it before I showed you the easy way. You know me, Casey. I'm not really a nice guy. Any other questions? Everybody's good? Okay. So, with that, then, remember, there will be a new quiz. I'll remind you at the end of class as well. There'll be a new quiz based off of homework 1. There'll be quiz 1. Actually, it should be available in my math lab right now. You go up here to quizzes and tests. You'll see there's quiz 1 at the top of the list. It says it is due on January 21st at 11:59 p.m. There is a 1 hour and 22 minute time limit. It's supposed to be an hour and 20, but I was too lazy to move my finger from the 2 all the way over to the 0. So you got an extra 2 minutes. Hey, when you're going through and doing like 17 of these quizzes and homeworks, okay, I'm just plain lazy, I'll admit. So anyway, you do get 2 attempts, but you can't just attempt each question twice. You have to do the whole quiz, then look at it. After each attempt, you can look back and it'll show you what you got wrong and what you had right. But you have to redo the whole quiz. You can't just go problem by problem. The system will take your highest grade. If something happened, like maybe the cat jumped up on your keyboard or something and locked up your computer and locked you out of one of the quizzes, let me know. I will open up another one for you. Be creative with your excuses, though. I got to entertain myself somehow. Yeah, it's unlimited attempts on the homework. Or actually, those are the tests. So you get an infinite number of attempts on your test.
Do the order of the questions change? I mean,
On the quizzes, sometimes they will from person to person, yes.
well, from attempt to attempt.
Oh, from attempt to attempt, they will change order too as well. The numbers will change too. They'll give you the same questions but different numbers. Okay, well then I think we should start on our new material for tonight. We talked a little bit last class about those 2 parts of a number, the count and the name. And we looked at different forms like whole numbers, integers, fractions, and decimals. Tonight we're going to look at algebraic numbers. Everybody starts to cringe. They don't hurt near as bad as it sounds. An algebraic number is just like any other number. It has a count, in this case the 4, and it has a name, the x. Now to understand algebraic numbers a little bit better, it helps to understand our number system a little bit better. You know, we talked about how 397 is just an abbreviation. It's really 3 hundreds and 9 tens and 7 ones. Well, where did these hundreds, tens, and ones come from? I mean, we talked about those are the names of our place value, but our number system is what we call a base 10 number system. What that means is the place values are actually powers or exponents with a base of 10. Now, if we had 8 to the 3rd power, that's an exponent. It means 8 times 8 times 8, which would be, what, 512. Well, our place values in our number system are powers. Although this one is a base of 8, our place values are a base of 10. It's 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so on. 10 to the power of 6 is 1,000,000. 10 to the power of 5 is 100,000. 10 to the 2nd power is 100. 10 to the 1st power is just 10. 10 to the power of 0. Anybody know what that is? Well, what place value is that in? Ones. Anything to the power of 0 is 1. The reason for that, we talked a little bit last week about patterns with multiplying negatives. Same thing happens here. That power means you're taking, the power of 2 means you're taking 2 tens and multiplying them together. Power of 4 means you're taking 4 tens and multiplying them together. Well, how do you take 0 tens and multiply them together? You can't. So the definition of a power, or the definition of an exponent, breaks down there. It doesn't work. So we have to look for a pattern. 10 to the 3rd power is 1,000. 10 to the 2nd power is 100. 10 to the 1st power would be 10. And what we notice there is when our exponent has a base of 10, every time our power goes down by 1, what happens to the result? It's divided by 10. It loses a 0. Divided by 10 is technically what's going on. So if we go one more step, 10 to the power of 0, what's 10 divided by 10? 1. So anything to the power of 0 is 1. So this is the ones, tens, hundreds, thousands, 10,000s, 100,000s, and so on. So we could have written this 397 as 3 times 10 to the 2nd plus 9 times 10 to the 1st plus 7. We don't usually write out the times 10 to the 1. We just leave it as just plus 7 or 7 ones. Well, in algebraic numbers, we might have something like this. See the similarities? Instead of the place values being 10 squared and 10 to the 1 and 1s, they're x squared and x to the power of 1, and x to the 0 would still be 1s. So our algebraic numbers are nothing more than numbers with place values that are variables. Now, of course, we can't abbreviate algebraic numbers. We have to write them out in full form like this so that we know what the place values are. Every digit has to have its place value written with it. So realistically, these algebraic numbers are very, very similar to our standard whole numbers. Couple little differences. One, as we said, is we always have to write them out in long form so that we have the place values written out. The second is, with our whole numbers or integers, either every digit is positive or every digit is negative. For example, negative 374 is a negative 300s. And a negative 7 10s. And a negative 4 1s. If the number is negative, every digit is negative. In an algebraic number, each digit can be positive or negative on its own. It's possible to have 7x squared negative 5x plus 13. That brings us to the third difference right there. Standard numbers and integers were restricted to 0 through 9 as our digits. In algebraic numbers, each digit can be as large as it wants to. That could be 452x if it wanted to be, because there's no carrying over from one place value to the next. So now as we work with these algebraic numbers, the same rules that we use for whole numbers is going to apply. If I just had a bunch of random digits thrown out here, like 8 10s and 7 1s and 5 10s and 300s. Is there anything I can do with that? I can combine like terms. I can combine digits that have the same place values. I have 8 10s and 5 10s. They could be combined. Now I should have had that as 3 10s instead of 8 10s. To give us 13 10s. Now since this is whole numbers, that 13 10s is going to have to be adjusted and the 1 is going to be carried. But the 7 1s and the 300s have nothing to combine with them right now. Algebraic numbers, the same is true. We might have 8x plus 7y plus 5x plus 2y. Same thing occurs. We have the 8x and the 5x have the same name or the same place value. We can combine those digits. 8x and 5x make 13x. We combine the counts. 8 and 5 is 13. And we keep the same name of x. Anything else we can combine? 7y and 2y is 9y. Now, we have to have something that links these digits together. Since that's a positive 9y, we put a plus in front of it. So it's 13x plus 9y. Yes, sir.
There was a minus in there somewhere. How would you go about that?
That's the next example. Good call. So let's say we have 17a minus 8b minus 14a minus 5b. Now we said that in an algebraic number, each digit can be positive or negative on its own. So this here can be thought of as subtracting 8b, but it can also be thought of as a negative 8b. So we can go to combine here. This is 17a. It's going to combine with the 14a, but it's not really 14a. It is negative 14a. 17 and negative 14 make 3a. We keep the same name. For b, negative 8 and negative 5 make negative 13b. Now, since there's a negative in there already, there's already a symbol in between them linking them together. So we just leave it like that. We don't have to add a plus in there if we don't want to. Now it can get a little more complicated than that. We can get into what we call polynomials, which are just the full algebraic numbers with more than one digit. You can see here this has got x's, or x squareds, x's, and then the ones. Now this looks ugly, and it kind of is, but it's no different than adding whole numbers or integers. We can set it up, making sure we line up the digits with the same place values. The 2x squared is going to go with the 4x squared. The negative 9x is going to go with the 7x, and the 4 goes under the 13. And we're going to add. Now, just like adding any other numbers, we're going to add down the columns. Negative 13 and 4 make negative 9. 7 and negative 9 make negative 2x. And then 4 and 2 make 6x squared. And we've just added polynomials. Now, I'm not going to spend a lot of time on that because that part's relatively easy. In fact, the way the book does it, the book tells you just eliminate the parentheses and combine like terms, which works. But what you're really doing is you're setting them up and adding the like terms, lining up the columns like you would with any addition. Where it gets tricky is subtraction. So here, we're subtracting polynomials. Again, these are just like any other numbers. We write them out, and we're going to line up the things with the same place value. So the x squareds go under the x squareds. The 4x's go under the negative 19x's, and the negative 11 goes under the 2. The difference is here we have to remember we are subtracting now down the columns. When I do this, I like to write things off to the side so I can see what's going on. Here we have 2 minus 11. So I'm right, 2 or minus a negative 11, I should say. So 2 minus a negative 11. What did we say we do when we subtract with negative numbers? Make it plus the opposite. So instead of 2 subtract negative 11, it's 2 plus positive 11. So 2 plus 11 is positive 13. Now we have negative 19 minus 4. We're going to change that to negative 19 plus a negative 4, which is negative 23. And of course, there's an x there. 3 minus 5, negative 2x squared. What do you think? Still better than a sharp stick in the eye? Some of you don't look so sure. Doing okay? That's the real trick, is when you're subtracting, if there's negatives there, don't do subtraction. Change it into addition and work with it that way. Otherwise, this is probably in the top two things that I see people mess up, is doing addition and subtraction with negative numbers. Yes?
Where did you get negative 19 minus 4?
Right there. It says negative 19x minus 4x. No problem. Okay, well, let's look at multiplying. We said that when we multiplied numbers, we combine the counts, and we also combine the names. That means we have 5 times 3, which is 15, and then we also combine the names. X times x is x squared. Now, unlike addition or subtraction, where we have to have the same name to combine numbers, in multiplication, we do not have to have the same name. I could have 4x times 7y, and this is still going to work. We're going to combine 4 times 7 is 28, and then also combine the names. X times y, xy. So 28xy. So when we run into numbers that have more than one name, we might have 9x to the third y times 2x squared y squared. We're going to combine the counts first. 9 times 2 is 18, and then we can combine the names. We can combine each name separately if we want to. X to the third times x squared is x to the fifth. Good. Y times y squared, y to the third. If you're wondering where that x to the fifth came from, we had x to the third, which is 3x's multiplied together, times x squared, which is 2x's multiplied together. If we multiply those together, we now have 5x's multiplied together, or x to the fifth. When you're multiplying variables with powers on them, you end up adding the powers. So something like this. Many of you have been taught that when you see something like this, you do a thing called distributing. When distributing works, it's a trick though, it's a gimmick. What you talk to with distributing is you go 5 times 3x is 15x, 5 times 7 is positive 35, and that's it. Well, what's really happening here is this is just a single digit number times a 2-digit number. It's just like taking 32 times 3. If I were doing that out by hand, I'd have 32 on top times 3. I'd do 3 times 2 is 6. 3 times 3 is 9. It's 96. Same thing would happen over here. The long way of doing this, that's 3x times 7 times 5. 5 times 7 is 35. It's positive, so I'm going to put a plus in front of it. 5 times 3x is 15x. So you can see it's just like multiplying whole numbers. So something like this, we've got 4x minus 8 times 9x. We don't have to line up the place values because we don't worry about that when we multiply. 9x times negative 8. Negative 72x. Good. 9x times 4x. Good. 9 times 4 is 36. And then we multiply the names as well. X times x is x squared. Or if you're distributing, it'd be 9x times 4x is 36x squared. 9x times negative 8 is a negative 72x. If you're used to doing it that way, I'm not going to stop you. I just want to show you this way for a while so you can actually see the real way of multiplying them out. In a little bit when we start solving equations and stuff, I am actually going to start doing them all that way as well, just because it saves a little time and it saves a little space. Yes?
Why is it square over here?
Oops. There you go.
Okay.
It's just not because I'm an idiot. There we go. Thank you. Any other questions? Okay. Well, what if it's something like this? Does that change anything? No. It'd be 3x squared minus 13x plus 2 times 4x, and we'd multiply it all out again. Now at this point, I'm just going to assume you guys see how you'd multiply that out. I'm going to start doing the shortcut and just distributing, just to save time. 4x times 3x squared. Well, 4 times 3 is 12. X times x squared, x to the third, x cubed. Now we're going to do 4x times, not 13x, but negative 13x. 4 times negative 13 is negative 52. X times x, x squared. Then we have 4x times 2, which is a positive 8x. And there it is.
Is that what's helpful?
That's coming up in just a second. Yep. In fact, let's do it now. What happens when we run into something like this? Well, this is exactly like taking something like 23 times 52. You would 2 times 3, then the 2 times 2, and then 5 times 3 and 5 times 2. Well, same thing here. 3x plus 7 times 5x minus 2. You're going to do negative 2 times 7 is negative 14. Negative 2 times 3x, negative 6x. Now, just like with whole numbers, when we moved over a spot, we had to leave a blank or a 0 down. 5x times 7? 35x. Positive 35x. 5x times 3x? 15x squared. And now you can see, just like with whole numbers, we can combine the columns, combine the things with the same place values. It's a negative 14, negative 6, and 35 is a positive 29x and 15x squared. Now you brought up FOIL. And that's the way most of us were taught how to do this. FOIL is an acronym where the F stands for first. You multiply the first two digits of each number. 3x times 5x is 15x squared. The O stands for outside. You multiply the outside digits. 3x times negative 2 is negative 6x. I stands for inside. You multiply the inside two digits. 7 times 5x, 35x. And L stands for last. 7 times negative 2 is negative 14. Notice, by the way, that's the exact same thing we got here. This just isn't organized even quite as neatly. But we were taught then that you have to go back and combine the things that are alike. So the 15x squared doesn't change, but negative 6 and positive 35x make 29x. And then we have the negative 14. We get the same answer. Whichever one's easiest for you is up to you. It doesn't matter. But I will show you an example here. Like this. FOIL doesn't work on this because this one's got a middle digit. This one would be Polynomial. But if we're doing it the long way with just long multiplication, it works just the same. We have the 3x squared minus 7x. Now, I'm not saying you can't do it with FOIL. Most of you know how to modify it and make it work. I just want to show you that long multiplication, it looks just like whole numbers. Do negative 5 times 9, negative 45, negative 5 times negative 7x. Positive 35x. Negative 5 times 3x squared. Negative 15x squared. Good. Now again, before we move over, we add a 0 there. 2x times 9, positive 18x. 2x times negative 7x, negative 14x squared. And 2x times 3x squared, 6x to the third. And now we can combine, adding down the columns. So we've got negative 45. 35 and 18, positive 53x. Negative 15 and negative 14 is negative 29x squared and 6x to the third. What do you think? More fun than a barrel of rabid monkeys? Debatable? That's why they're rabid. They're not much fun at that point. If I just said a barrel of monkeys, it'd give me a run for my money. Or we can have something like this, where we're dividing. Now, I know he's looking, that looks like a fraction. It is, but fractions and division are kind of interchangeable. A division problem can be written as a fraction and the other way around. So this is 21x to the third divided by 7x squared. Just like multiplication, we combine the counts. 21 divided by 7 is 3. Then we combine the names. Well, we have x to the third, which is 3x's multiplied together. X squared, which is 2x's multiplied together. We can cancel out 2 of the x's to leave us with just an x. Or for those of you familiar with powers and exponents, you just subtract the powers. 3 minus 2 is 1. So we might have 36x to the fifth divided by 9x squared. What do we do first? 36 divided by 9 is 4, and then x to the third. X to the fifth divided by x squared is x to the third. Again, subtract the powers. 5 minus 2 is 3. We're going to have this one. We have more than one variable. 51 divided by 17. 3. X to the 8th divided by x to the 3rd. X to the 5th. Y squared divided by y? Just y. There we go. What do you think? Questions? You good? Okay. We can run into polynomials, multiple digit numbers divided by a single digit number. If we had 936 divided by 3, one of the ways to do that is to divide each digit. 9 divided by 3 is 3. 3 divided by 3 is 1. 6 divided by 3 is 2. Now, obviously, with whole numbers, they don't work out quite that simple all the time. But with the polynomials we're going to do, they will. Something like that. We divide each digit. 12x squared divided by 3 is 4. Negative 9x divided by 3. Negative 3x. 24 divided by 3. Positive 8.
We ever have to do the 4x and the 3x, and you have to figure out what the 9 is, like 3 and 3, and then you have to split it out that way?
No, we're not going to get into factoring polynomials like that. No, that would be more of a college algebra or a tech math or something like that. Not unless you're really upset me. We don't do that.
No quadratic formula.
No quadratic formulas or anything like that. Like I said, unless you really make me mad. So if you really don't want to see, well then on we go. The next step, really kind of what's important to us as far as working with algebraic numbers, is things that look like this. Equations. X equals 7, or a variable equals a number, is an equation. And all equations start out like that, as a variable equals a number, or vice versa. And they're built up from there. To understand how these equations work, we need to understand, of course, that symbol right there, which is the equal sign. What does it mean? Well, it's almost so common it's hard to define, doesn't it? It means equals. What does equals mean? They're the same. Okay, what it means is what's on one side has exactly the same value as what's on the other side. In fact, we can think of it as being a balanced scale, like that. What's on one side has the exact same weight as what's on the other side. And like I said, all equations start out like that, as a variable on one side and a number on the other. And they're built up from there. One thing we could do to build onto this equation is we might add 4. So now it's x plus 4. But if we add to one side of this scale, it's going to start to tip. So how do we keep it from tipping? We add to the other side. We have to do exactly the same thing to the other side of the scale to make sure it doesn't tip. So over here, 7 plus 4 is 11. So now when you see an equation, the command you're going to be given is solve. What does solve mean? Well, solve for x, yeah. What solve means is it's telling you, take this equation back apart. Well, this equation was built by adding 4. How are we going to take it apart? Subtract 4. Subtracting 4 takes that piece off, leaves it with just x. But again, it's going to cause that scale to tip unless we do exactly the same thing to the other side. We know the equal sign separates the two sides, so we have to subtract 4 over on the other side of the equal sign. 11 minus 4 is 7. So x equals 7 is the solution, or the solved equation. Now that one was easy because we watched it be built, so it was easy to take it apart. The tricky part is to look at an equation and figure out how it was built. To do that, and I know most of you looked at this one and already have the answer for it, but let's go through it step by step. To figure out how it was built, we first find the equal sign. There's the equal sign. Then we identify which side of the equation, if it is just one side, has the variable on it. And in this case, it's this side that has the variable. That's the side that's going to tell us how it was built. Remember, the equation started out with the variable over there all by itself. So whatever's keeping the variable from being by itself is what was built onto this. Well, what's keeping y from being by itself? The 7. And what operation was used to combine this with the y? Subtraction. So this equation was built by subtracting 7. Well, how do we take that apart? Add 7. Adding 7 takes that piece off. It's gone. And we're left with just y. But remember, to keep that scale balanced, we have to do the exact same thing to both sides. So we added 7 over here. We add 7 over here. 8 plus 7 is 15. Now, if we get to this point and we're unsure of ourselves, we can always go back to the original equation and replace the variable, in this case the y, with the number that we solved for. If y equals 15, putting 15 in here where the y is better make this true. So if we replace y with 15, it's 15 minus 7, which is 8. We have the same value on each side of the equation, so that is true. So we might have 7z equals 42. How is this one built? Exactly. Here's the equal sign. There's the variable. 7 is keeping z from being by itself. It was multiplied to build it on. So to take it apart, we're going to divide by 7. It's now gone. Leaves us with z. Over here, we divide by 7. 42 divided by 7 is 6. Now, these are not always going to come out so nice and pretty. I'm using examples that have integer answers in just to make it easier on myself in class. But we may have something like 58 equals 7y. What are we going to do to solve that? Divide by 7, giving us y here. We have to divide over here. 58 divided by 7 is approximately 8.2857143, approximately. So be prepared. You will get decimals or possibly fractions. Don't worry, it's not contagious.
No, it's just
There was none. Give me a number between 20 and 50.
20, 50.
Yeah. 17. Okay. It's not quite between 20 and 50, but it'll work. 17 divided by 7. Dividing by 7, that would be 2.4285743 approximately.
Okay, I'll just keep your order on it.
You can check it on the calculator if you want to.
That's right.
Yeah. Math is all about patterns. Now, I've done math pretty much every day of my life for about 19 years now, which means I'm either really insane or I'm starting to get good at it, or both. Don't rule that out. Once you start seeing the patterns, the calculations are really easy. I mean, I can rattle off some really ridiculous calculations just because once you start doing the first couple of digits, start to see the pattern, you can just go with it.
I can do that, but I can do it in my head. I have to write it out.
Sure. Well, like I said, after a few years, you start. Of course, I'm getting to that point now where I'm starting to forget where I left my shoes. So I'm sure the patterns are going to start disappearing for me. But just wait, you guys will get there someday. I'm only 41. Okay, so let's look at this one. So here we find the equal sign. We identify which side is the variable. That's over there. This time there's two things that are keeping our variable from being by itself. We have the 5 and we have the 3. What operation was used to build the 5 on? Multiplication. How about the 3? Subtraction. So now we have to ask ourselves, when this was built, what was done to the variable to build this? Which one happens first? Order of operations, do we multiply or subtract first? We multiply first. So when this equation was built, the x was multiplied by 5 first, then 3 was subtracted from it. That's how the equation was built. Now if you put something together, let's say you just put the last piece on it, and now you're going to take it back apart. What's going to be the first piece you take off? The last piece that was put on. So the last piece that was put on here was subtracting 3. So the first piece we're going to take off, we're going to add 3. So that's gone. Leaves us with just the 5x. Doing the exact same thing to the other side. 42 plus 3 is 45. And now all we have left to take off, divide by 5. X equals 9. 45 divided by 5 is 9. You are correct. So on this one, what would I do to start solving it? Subtract 2. So 50 equals 7x. And then divide by 7. Anybody want to erase me? X equals 7.142857 approximately. Okay. Maybe you want me to start going more than 6 digits on my calculations, by the way. Sorry. Anyway, I'll be nice. Something like this. We find our equal sign. We go to identify which side the variable's on, and we find ruh-roh, there's a variable on each side. We can't solve this the way it is. We have to adjust this equation. What we have to do is we have to get rid of one of the variables. We cannot solve an equation, even if it's the same variable, we cannot solve an equation with 2 variables in it, even though it's the same one. Since they're on opposite sides of the equal sign, we can't combine them. So we're going to have to just get rid of one of them. And what we usually do is we get rid of the smaller one. And literally what we do is we grab onto it and we just take it off. Well, mathematically, how do we do that? We subtract. It's a positive 3x. We subtract 3x, and that makes it go away, leaving us with 23 over here. Well, we have to take 3x off the other side, and the only thing we can take it from is the 7x. We can only subtract from things that have the same name. 7x minus 3x is 4x. Is that it? You still have that positive 5 there, the plus 5 there. Now we can start taking this equation apart. What are we going to do? Subtract 5. 4x equals 18, and then divide by 4. X equals 4.5, or 4.5. Now again, if we want to double check our answer, we can go back up here. We can replace x with 4.5. So 7 times 4.5 plus 5 equals 3 times 4.5 plus 23. 7 times 4.5 is 31.5 plus 5 is 36.5. 3 times 4.5 is 13.5 plus 23 is 36.5. And get the same value on each side. I know that was the correct answer to that equation. So this one, x appears twice again. What's different about this one? They're both on the same side of the equation. Here's our equal sign. Both x's are over here. So that means I can take both of them and I can just push them together and make one big pile. In other words, I can combine them and it won't affect the way the equation balances. So I can do 4x and 5x make 9x. I still have that plus 7 there, equals 53. Now what do I do? Subtract 7. 9x equals 46, and then divide by 9. X equals 5.111111. Or 5 1/9 if you prefer fractions. Any questions? The only problem with these repeating decimals is you can't put them back in to double check because they're rounded off. You know, 5.111111 is rounded off, so it's not going to be exact if we put it back in to double check that. So you'd have to use the mixed number. You have to use the fractions if you wanted to double check it and get an exact answer. Otherwise, you can just double check it, and if you come out really, really close to the same on both sides, maybe trust it, but you can't be totally sure that way. What do we see on this one that's new? Parentheses. And from our discussion on order of operations last week, we know that whenever we see parentheses, it should scream at us, do something here first. First question is always, is there anything in the parentheses that needs to be done? And in this case, there's not. 2x minus 7, there's nothing to do there. That's just a two-digit number. It's an algebraic number. So all that parentheses there is doing is it's not giving us, it's not an enclosing symbol telling us we have to work inside it first. It's separating out that number. So if there's nothing to do inside the parentheses, the second question is there anything that needs to be done to the parentheses? And there is. It's being multiplied by the 5. So we're going to multiply the 2x minus 7 by 5. We can either write it out the long way, like we showed you, or I can just distribute. For the sake of space and time, I'm going to distribute.
So you could do that and use divide by 5.
Well, you could, but it's more technically accurate. There are times where you get in trouble doing that. I'll show you one. I'm going to do 5 times the 2x is 10x. 5 times the negative 7 is negative 35 equals 25. Now what do we do? Plus 35. Good. 10x equals 25 plus 35 is 60. And then divide by 10. X equals 6. And you can double check if you want to. Put a 6 in here. 2 times 6 is 12 minus 7 is 5. 5 times 5 is 25. So we're good. Now you said you maybe could have just divided by 5 to start that off. Well, sometimes that doesn't work quite so well. We can run into something like this.
Yeah. 7 divided by over 3.
Yeah. So you could do it if you really want to go through. It gets to be a little bit of trouble. The simpler way to do this is just to go ahead and go through the steps. When we see something like this, here's our equal sign. We have the parentheses over here. We can work with one side of the equal sign at once if we want to. So we just work on the left side here. Anything in the parentheses that needs to be done? No. How about to the parentheses? Yes. Times 3. 3 times 5x? 15x. 3 times negative 3. Or 3 times negative 1. That might be negative 3. Now the parentheses are done, so we don't need them anymore. Got the plus 7 there. We can still combine a negative 3 and a positive 7 to get positive 4. That, of course, still equals 34. And now we solve by subtract 4. 15x equals 30. And then divide by 50. X equals 2. Questions? Okay, well, let's stop there for now. We'll take our break. We'll come back at about 6:30 and start up again.